This video can assist you in learning what you need to know about Newton's first law of motion. What we're going to do is go through the laws first in terms of just what they state, what they mean, how they apply to the motion of objects. And then next week, you'll learn the math that goes along, in particular with Newton's second law, how to use the force equation, and how to calculate momentum and changes in momentum. That's the equation part of this particular unit. So Newton's first law, it states objects in motion stay in motion, objects at rest stay at rest, unless a net force acts upon them. The classic way of stating or phrasing Newton's first law. If you want to pause this while you write this down, go ahead and hit pause. What this means in kind of more plain English, or at least in terms of how it applies to what we've been talking about and what we've been learning, is to say in the absence of a net force, the motion of an object is constant. So we've spent a little bit of time working on forces and net forces. Net forces, as you know, are when the forces that are acting on an object, the gravity, the normal force, the applied force, all that stuff, fails to cancel out. And you have something left over. That something left over is a net force. And what this law says is in the absence of a net force. So in other words, they all do cancel. There's nothing left over. There is no net force. When all the forces acting on an object cancel out, the motion of that object is going to be constant. So again, if you want to pause this, go ahead and pause this and write that down. That's going to be kind of the way you want to do this as we go through. If there's something you want to write down, just hit the pause button, write it down. And when you're ready to resume, just resume it. So in the absence of a net force, the object's motion is constant. So if it is in motion, if that object is moving, its velocity will be constant. And velocity is the correct word to use with this. It's not just speed. We can't say its speed is constant because, as we know, it's more than that. Velocity is speed and direction of an object. So if it's in motion, its velocity will be constant. Again, that means its speed and its direction will be constant. The object in question would move at a constant speed and in a straight line if there are no net forces. If there are no net forces acting on an object, the object's speed will stay constant and it will move in a straight line. Again, that's if there's no net force. If there's either no forces acting on the object at all, or if the forces that are acting on the object completely cancel out. Now, honestly, there are very few examples of this that you could actually see in real life. If you had a perfectly controlled environment and you dropped an object, it might follow Newton's first law. We know as the object falls, the force of gravity will be pulling down on it. And there will be an upward force resisting gravity because there pretty much always is. In this case, it'll be air resistance. We wouldn't have friction because there's no surfaces rubbing together, but it is falling through the air, so there would be some air resistance going on there. And if those are the only two forces at play, when the object finally reaches something called terminal velocity, that's its fastest free fall speed, the force of gravity and the force of air resistance would be equal. It's called terminal velocity, and it happens when the force of gravity is equal to the force of air resistance. Those forces would be equal in size, opposite in direction, and they would cancel out. So it would be as if there were no forces acting on the object. This, again, would have to be in a very controlled environment You'd have to do it with an object like a ball that isn't going to be subject to twisting and turning on its way down. It kind of has to fall straight down for this to work. There can't be any cross breezes or anything like that, because then that messes the whole thing up. And it applies the net force to the object and it won't move in a straight line anymore. It works fairly well in the short term. Again, even this isn't the best example in the world. You could talk about something like the Voyager space probes that are outside of the reach of our sun. They're outside of our solar system now. So they're basically traveling in interstellar space. They'd be moving at a straight line and a constant speed because there's nothing really affecting them. There's no real forces being applied to them. So since there's no forces being applied to them, there is no net force. And they will move at a constant speed and in a straight line. But again, a very difficult one to find an example for, because it's just, there's so much that interferes with motion on Earth. This law does really apply more to stationary objects. Objects at rest will stay at rest. That part's easy enough to understand. If you have a book sitting on a shelf, it'll just sit on the shelf. The force of gravity is being balanced out by a normal force, and it's not going to go anywhere. It's not going to do anything. First law is also called the law of inertia, because what an inertia does is measure an object's tendency to resist changes in motion. Every object has inertia. Every object wants to follow Newton's first law, continue to do what it's doing, whether it's at rest or in motion. It wants to continue its current state of motion. And what inertia measures is how good it is at doing that, how good it is at maintaining that motion, how good it is at resisting any changes to it. Something that has a lot of inertia is very difficult to change the motion of. It's hard to speed it up, slow it down, change its direction, that kind of thing. Something that has very little inertia, it's very easy to change its motion. It doesn't resist that change very much. The inertia of an object depends on its mass. That's the one factor that determines how much inertia an object is going to have. If an object has a high mass, it'll have high inertia. So something like a wrecking ball, those big metal or concrete balls they put on the end of chains and swing at buildings to knock them down. A wrecking ball has a lot of mass, and because of that, it has a lot of inertia. It's very hard to change its motion. It's very hard to stop its motion, etc. So when they get that wrecking ball swinging towards the building, it's very difficult for the building to stop it. So it tends to just move straight through the wall and knock it down. Trains, freight trains have a lot of inertia. A freight train has a lot of mass. And because it has a lot of mass, it's very, very hard to stop it. Very hard to turn it. It's difficult to change its motion because it has so much inertia. You've probably heard it can take a train up to a mile to stop. It's because of all the inertia it has. It's a tremendous amount of mass. It can be upwards of a mile long. All those cars, all that mass, tons of inertia. Stopping it is very difficult. Again, when something has greater mass, it has more inertia, so it's harder to change the motion of more massive objects than it is for less massive ones. And some of the examples that I like to use are very common sense ones, things you experienced before. I like to talk about shopping carts, buggies, if you call them that. When you first go to the grocery store to get groceries and the shopping cart is empty, really easy to push, really easy to turn when you get to the aisles. You have no problem maneuvering that empty shopping cart around. But you start adding more and more stuff to the shopping cart, the mass of the cart system goes up and up and up. And by the time that shopping cart is full, it's a lot harder to push. It's a lot harder to get moving. It's a lot harder to stop. It's a lot harder to turn. Classic example of inertia. When it's empty, it has low mass. It has low inertia. It's easy to start. It's easy to stop. It's easy to turn. When the shopping cart is full, it's got high inertia. And as a result, it's much harder to change its motion. And we play baseball with baseballs, not bowling balls. A baseball has a relatively small mass, so when you try to hit it with a bat, it's relatively easy to change its motion. It's relatively easy to stop its motion in one direction and accelerate it in the other. It's really easy to change its motion because it has low mass. If you tried to throw a bowling ball and hit it with a bat, it's just going to break the bat. The bowling ball has far more mass than what the baseball does. And because of that, the bowling ball has much more inertia. So when you hit it with the bat, it tends to just go through the bat. It breaks the bat because you're not going to change its motion. You're not going to change its direction, its speed too well with something as light as a baseball bat. Again, more mass for the bowling ball. It means it will not change speed or direction as easily as a baseball does. Another classic example that I like to talk about, it works well in physics classes because a lot of you have cars, think about cars, want cars, that kind of thing. That's why trucks have larger tires and brakes than what regular sedans, four-door passenger cars, or two-door passenger cars do. Literally, the smaller the car is, the smaller the tires, the smaller the brakes. The bigger the vehicle is, the bigger the tires, the bigger the brakes. And this is an inertia thing. Trucks have a lot more mass than what small cars do. So trucks are a lot harder to turn. They're a lot harder to stop. You need much bigger brakes. You need much bigger tires in order to apply much greater forces in order to get that to happen. Small cars need small tires, small brakes because it's easier to change their inertia. It's easier to start them. It's easier to stop them. It's easier to turn them. And this all plays into why cars get much better gas mileage than trucks do. You buy a car, you can get something that gets over 30 miles per gallon. You buy a truck, you're going to get, if you're lucky, 12 miles per gallon, less than half of what the car is going to do. And it's all about inertia. That truck weighs so much more. It's a lot harder to get it started. It's a lot harder to get it going. It requires bigger engines. It requires more fuel. The little car gives you much better gas mileage because it's got less mass. It's got less inertia. It's easier to get it moving. It's easier to get it rolling. It's easier to speed it up. They're cheaper to maintain. When you need new tires for a car, it's a lot less expensive than buying new tires for a truck. The car needs smaller tires. It applies less force. It's got less inertia. It doesn't take as much to start it, stop it, get it going, turn it, etc. Brakes are cheaper. I mean, it's all factors in. This is all inertia based. It's all understanding how the inertia comes into play. Driving them is significantly different. You can take a turn much faster in a car than you can in a truck. The truck has more mass, it has more inertia, so it just wants to keep going straight. You turn the wheel and the truck wants to keep doing what it's doing. It wants to follow Newton's first law. It wants to go in a straight line at a constant speed. So you really have to slow that truck down. You really have to reduce what's called its momentum in order to get the thing to turn. It's all this inertia-based concept. It's all the same idea here. Now, I do want you to understand mass and weight are related, but they're not the same thing. On Earth, you can say an object that has more mass will weigh more. On Earth, something is heavier because it has more mass. Something would be lighter, have less weight because it has less mass. They are related, but they're not the same thing. And this is why this is important. As we think about physics, we don't want to think about just life on Earth. We want to be able to apply our physics anywhere, any place, any time. And one of the places that comes up is outer space. An object in space may have no weight. If it's not under the influence of gravity of any planet or star or whatever, it would be weightless. But that object that's out in space would still have all the mass it had on Earth. The mass doesn't change. Weight changes when gravity changes, mass does not. So it's important to understand that inertia is a mass-based concept, not a weight-based concept. You can get rid of gravity, you can get rid of weight, but you would still have inertia because your object would still have mass. And that's what I want to get at here. Objects that are weightless, objects that are not under the influence of gravity, would still have mass. And as a result, they would still have inertia. This is the question that I get asked a lot. Can you lift heavy things in space? Could you push a 1-ton chunk of rock in outer space? Again, the misconception is because there's no weight there, that rock doesn't weigh anything, so you should be able to pick it up with one finger, push it around with one finger, etc. And the answer is no, you couldn't do that. It would not be easy to do. There are some things that would change about it. You wouldn't have any friction. You wouldn't have any air resistance to overcome. But the problem is you would still have every bit of inertia that you have on Earth. It's still going to resist changes in motion. You would push on that rock. So let's say the rock is here in front of me. You would push on the rock, but what would really happen is you would just push yourself backwards away from the rock. You would push on the rock, and the rock itself really wouldn't do anything. It would stay right here. But what you would do is you would push yourself backwards and float away from the rock. So it would look like the rock was moving, but what would really happen is you would be moving backwards away from that rock at a significant speed. If the rock moved at all, it would be very, very, very slowly. So again, no, it's important to understand mass and weight are two different things. Weight is really just the pull of gravity on an object. We'll learn to calculate that next week. Mass is something entirely different. Mass is how much matter there is, how many atoms or molecules there actually is in that object. When you leave Earth, or even when you climb to the top of a mountain, weight changes. Your weight will decrease the further away from the center of the Earth you move. You actually do weigh less at the equator than you do at the poles because the Earth kind of bulges. It's not a perfect sphere. At the equator, you're actually further away from the center than you are at the poles. So you'd actually weigh less at the equator, and it would be a measurable amount. But the problem is everything still has all the same old inertia it always has. Again, outer space, you can get rid of the weight entirely, but all that inertia would still be there. The trick question I used to like to ask students a lot is, would you rather be hit by a space shuttle when it's flying in space or a space shuttle when it's landing on Earth? And everybody always said, I'd rather get hit by it in space. And again, it's that misconception that because it's weightless, it wouldn't do anything. Now, you'd be a bug on the windshield no matter what. You'd be splatted by it no matter what. It would still have all the mass it has on Earth when it's up in space. It still has all the inertia it would up in space that it did on Earth. And it would have the same effect on other objects. It would do the exact same thing to you in space as it does on Earth because the inertia would be the same. And again, if you tried to push on a 1-ton boulder in space, you just push yourself backwards. That's Newton's third law. We'll talk about why that happens when we get to the third law. But you just push yourself backwards. That's all that would happen. If the rock didn't move forward, it would just move forward very, very, very slowly. And that's only because there's no friction, there's no air resistance up there to stop it. On Earth, it wouldn't move at all because there'd be friction there, and they wouldn't be able to push hard enough to overcome that friction. But in space, because there is no friction, it may move a little bit, but by far and away, you're going to move more. This is another thing. This is actually one of the misconceptions that I blame on science fiction movies. Do spaceships need engines? When you watch the space movies, whenever the spaceship's flying by, the engines are always on. You always hear the roar of the engines. And that is a complete fallacy. A spaceship does not need engines to stay in motion. There's no friction. There's no air resistance. The two big things that produce those net forces on Earth that stop the motion of objects. So because you have no friction or air resistance, there is no net force acting on those spaceships. So they do follow Newton's first law. They will move at a constant speed in a straight line. I mentioned the Voyager space probes earlier. They were launched in the 1970s. They have left our solar system, and they'll go on forever. They'll travel forever in a straight line, in a constant speed, until they hit something, or until something finds them and takes them. they will fly in a straight line forever because there's no friction or air resistance to produce a net force. They don't have engines on them that are firing. They don't have rockets that are going. It's just Newton's first law. They are in motion and they will stay in motion because of it. And satellites. Satellites orbit Earth all the time. They're out there in motion all the time, and they don't have rockets firing all the time. They have engines on them. They use those engines to boost them up into higher orbits because they'll slowly, gradually move towards the Earth as they orbit it. They will fall and spiral into it. So they'll fire those engines on occasion to push them back up where they belong, but they don't have to fire engines to keep them going. It's Newton's first law. There's no net forces acting on them, so nothing to slow them down, no friction or air resistance to slow them down. Spaceships only need engines to change their direction, speed up or slow down, to accelerate. So could we launch a rocket and get it to the next closest star? Absolutely. Because we don't have to have fuel to get us there. We just have to point it in the right direction and give it a good push. It'll keep going in that direction until it hits something or until we stop it. We just can't do it because it gets there too slow, because we can't go fast enough. Let's relate this back to free body diagrams. In a free body diagram, Newton's first law would be any free body diagram that you draw in which there is zero net force. If you think back to all those free body diagrams you looked at and all those net forces you calculated, anywhere that you had a net force of zero, that would fall under the jurisdiction, if you will, of Newton's first law of motion. Anytime the net force was zero. So we have a 15 Newton box sliding to the right across the floor. An applied force of 10 newtons is countered by a 10 Newton force of friction. So let's go ahead and draw the free body diagram for this. Again, free body diagram is always a box, no matter whether it's a box or an airplane or a car or whatever. The box is 15 newtons. That's the weight of the box. That's our gravity. We know it's sitting on the floor. So whenever an object sits on the floor or on any kind of surface, there's going to be a normal force that counteracts gravity. And that's what it's going to do. It's going to push upward with a 15 Newton force to counteract gravity. And again, what that force just does is keeps it from sinking into the floor. Keeps it from falling to the center of the planet. We have an applied force. Okay, it is sliding to the right. That means it's moving to the right. So my applied force has to be in that same direction, the same direction as its motion. So that's FA. Let's go ahead and label these for practice. That's force of gravity. That's normal force. And again, the applied force is what's keeping it moving. It's moving to the right, so the applied force is to the right. It's in the direction that's moving. Applied force is always in the same direction that the object is moving. We have a 10 Newton force of friction. Friction always opposes motion. So friction always goes in the opposite direction. So it would go this way, 10 Newtons. That's our free body diagram. And again, as we know, when forces are in the opposite directions, we can add them, we can subtract them. When they're in the same direction, we add them. So my gravity and my normal force are in the opposite direction. We will subtract those. 15 minus 15 is 0. Again, the other way we can look at that as upward being positive, downward being negative. So it's positive 15 plus negative 15. Again, 0 in the vertical. These are in opposite directions, the applied force and the force of friction. So we subtract them. 10 minus 10 is 0. Or again, right is positive, left is negative. So negative 10 plus positive 10 is 0. No matter how you cut it, the net force is 0. Now, because the net force is 0, we know Newton's first law applies. And the first law tells us that an object in motion will stay in motion. If it's moving, its velocity will be constant. So we can look at this free body diagram, see that there is no net force at play. And because there's no net force at play, we can say this object will continue moving to the right at a constant speed. And that's how we do it. It just adds another layer onto the net force calculations onto the free body diagram. So you start with the free body diagram. You look at all the forces that are acting on the object. You try to find the net force of the object. And if you come across one where the net force is 0, then you know that's Newton's first law. And so whatever it's doing, it's going to continue to do. There will be no changes in motion. There will be no acceleration. So it'll have a constant speed and it'll continue moving in the same direction that it was moving in. And that's just the illustration that I just did. The downward force, that was the weight of the object. It was a 15 Newton box. So again, that's gravity. That's the weight of the object. That's the normal force. Counteracting gravity is sitting on the ground, so the ground will push up on the box, counteracting the gravity, keeping it from sinking into the ground. This would be the applied force, because applied force is always in the direction of the object's motion. This would be the friction. This friction opposes motion. It's always in the opposite direction that it's moving in. All those cancel out, so the net force is 0. So it will continue to the right at a constant speed. So this one, a 5 Newton book sits stationary on the third shelf of a bookcase. We're going to do the free body diagram for the book. 5 newtons, again, that would be the weight of the book. Newton is the metric force unit. It's how we would use pounds in the United States. So a 5 Newton book is like saying it's a 1.2 pound book. It's talking about the weight. That's the gravity part. So we know we have a downward force of 5 newtons. It's sitting on the third shelf of a bookshelf. That means this shelf has to be pushing up on it with a 5 Newton force. So we get this. Again, free body diagram. It's a box to represent the object. That's the book. This is the force of gravity pulling down on it. This is the force of the shelf pushing up, or the normal force, as we call it. They're in opposite directions, so we can subtract them. 5 minus 5 is 0. So again, just add them up using positive for the upward, negative for the downward. Positive 5 plus negative 5. Still get 0 no matter how you cut it. So we know this is an example of Newton's first law. Now this is an object at rest. It's sitting stationary. So what we can say is it's going to continue to remain at rest. It's going to remain stationary because those forces cancel each other out. Now the next question might be, what if this force of gravity were stronger than the normal force? What if gravity was pulling down with a 6 Newton force, but the shelf could only push up with a 5 Newton force? Well, the answer to that is Newton's second law. Whenever the forces don't cancel, whenever you do get a net force, that's when you move from the first law into the second law. That's where we will pick up with the second video. Now, what we're going to do for this unit in terms of a quiz grade is you're going to be, as you go through these laws, trying to find a good example of each one. And then you're going to write me a paragraph to explain how that example relates to the law. And considering everything that we talk about, everything that you have to learn about, everything that you need to know about in terms of that law. So your assignment would be to scour the internet and find yourself a good example of Newton's first law. You'll need to have a picture of that law, and you'll need to write up an explanation. And again, the explanation should be written in the form of a paragraph, and it does need to give good detail on exactly how this relates to the law. This is the first law, so it can be an object at rest or it can be an object at motion. You decide. But again, it has to be written up with a good, thorough explanation of how that picture you've chosen applies to Newton's first law. You're going to do one of these for each of the laws. You're going to make me a little poster. I'm going to grade it according to the rubric that I'm going to give you, and that is going to be your quiz grade for this part of the unit for the 3 laws of motion.